Our next speaker is Vinesha Peiris from Swinburne University of Technology. Please, Vinesha, go ahead with your presentation.
Thank you, Vera. So my name is Vinesha Peiris. I am a PhD student from Swinburne University of Technology. So today I am going to talk about rational approximations and their applications in neural networks. So this is my outline for today. I have three main sections. So in the first part, I will be talking about uniform approximations, mostly focusing on rational and generalized rational approximations. And of course, I will talk about bisection method and the differential correction method, which can be actually used to find rational approximations in uniform norm. And then I will move on to applications in neural networks. So this is where we actually see the contributions of rational functions and uniform approximations in the context of neural networks. And I finally have some numerical experiments. So in uniform approximation, we are actually trying to minimize the maximum deviation of the approximation from the original function. So uniform approximation is also known as Chebyshev approximation, approximation in uniform norm or in Chebyshev norm. So this is the formulation of a uniform approximation problem in general. So we have this function f of t, which is my original function, which is a univariate function. And then I have psi of a t, which is my approximation. So this t in psi of a t is the same t as in f of t, and capital A consists of the parameters that we can change. So we are looking for the set of parameters that could give us as best as possible approximation in uniform norm. So we are trying to minimize or reduce the worst error in our approximation. So this approximation psi of a t may be a polynomial, a piecewise polynomial, a trigonometric polynomial, or even a rational function. So we are actually interested in the case where this approximation is actually a rational function. So in the case of generalized rational uniform approximations, we have a ratio of two linear functions. Now I have my parameters, capital A and capital B. They are coming from the numerator and the denominator, and they are subjected to optimization. And then I have gt and ht. They consist of the basis functions. And here we are actually not restricted to monomials. We can actually have any function of t here in the basis functions. We only need my numerator and the denominator to be linear with respect to its parameters. So I need this numerator to be linear with respect to capital A, and I need this denominator to be linear with respect to capital B. So we basically have a ratio of two linear functions. And of course, I want my denominator to be positive, and we usually fix one of the terms in the denominator so that we can actually avoid having two optimum solutions which are multipliers of each other. And this is also known as the normalization condition. So one very well-known example for the generalized rational approximation is the classical case where we have a ratio of two polynomials. Now these basis functions, they are just monomials in this case, so t to the power i's. And we have ai's and bj's, they are the parameters coming from the numerator and the denominator, and of course they are the coefficients. And we usually fix B naught so that we can actually avoid getting two multiple optimum solutions if they are multipliers of each other. And this is again known as the normalization condition. So the objective function of the generalized rational approximation, so this f of a b, this function is actually quasi-convex. I hope you all remember the definition of a quasi-convex function. So we say that a function f is quasi-convex if its domain and sublevel sets are convex sets. So this is actually a more general class of functions than convex functions. So this objective function actually forms a quasi-convex function. And let me actually point this out to you. So this ratio, where we have a ratio of two linear functions, this ratio actually forms a quasi-affine, which is also known as quasi-linear function. So you can actually figure out the proof by using this fact. So I'm not going to walk you through the proof. So this property, quasi-convexity of this function, is actually very important, and we can actually apply the bisection method to find my rational approximation by using this property. So before I move on to the bisection method, let me reformulate my problem. So I have my original problem here, and I'm going to take this maximum absolute deviation to be this variable set, so we can come up with these inequalities. And this reformulation is called problem 1, because I will be using problem 1 in the upcoming slides. So this original problem and this reformulation, they're actually equivalent. Okay, moving on to the bisection method. Now, this method is actually developed to find solve quasi-convex optimization problems in general. And this method actually relies on solving a convex feasibility problem at the midpoint of the bisection interval. And this is actually the most important step of this process. And in some cases, solving the convex feasibility problem is not as easy as we think. But luckily, in the case of classical and generalized rational approximation, this convex feasibility problem can be reduced to solving linear programming problems. So it actually makes our lives a bit easier. So we only have to solve a linear programming problem. Now, in the algorithm, you have to actually start by specifying your upper and lower initial values for the interval. And then you have to fix set at the midpoint of this bisection interval. And then you have to check if problem 1, which is my reformulation coming from the previous step, previous slide. So you have to check if this problem 1 has a feasible solution. If there is a feasible solution, you can update your upper bound, or else you can update your lower bound. And you have to continue this process until the gap between these two bounds become really very small. Okay, moving on to the differential correction method. Again, another very important and interesting method to find rational approximations. And there are several versions of this method. So the original version is developed by Henry L. Loeb and E.W. Cheney in 1961. And later, slightly modified versions were also published. And I have included this reference where they actually talk about the convergence of the original differential correction method. So it is actually a very nice paper if you want to learn a bit more about the differential correction method. Now, this algorithm is an iterative process. So at the kth step, you have to find your numerator pk and denominator qk, and you have to find them by minimizing this expression. So this expression is actually coming from the original differential correction method, and in the modified versions, they actually have a slightly different expression here to be minimized. So the normalization condition that they use here is this one. So you are basically trying to force all of your coefficients in the denominator to be within the interval -1 and +1. And in this expression, we have delta k minus 1 and qk minus 1. So this delta k minus 1 is the maximum absolute error coming from the previous step. And qk minus 1 is the denominator coming from the previous step. So this differential correction method and the bisection method, they both use linear programming techniques in their subroutines, but they have slightly different normalization conditions. So for differential correction method, they actually force all the coefficients of the denominator to be within this interval. But for the bisection method, you can simply fix the coefficient of the lowest degree monomial so that it actually makes sure that we are not getting two optimum solutions if these two solutions are multiplies of each other. Okay, moving on to deep learning. So this is actually a branch of machine learning, and it was inspired by artificial neural networks. So in a neural network, we have layers of nodes, and we have input layers, hidden layers, and output layers. And you can actually have one or many hidden layers or no hidden layers at all. And these nodes are actually connected, and these connections are known as weights. Now, let me actually show you a model of a very simple neural network which has no hidden layers at all. And there is just one output node in my output layer. So suppose I have simple n number of inputs. So I have simple n number of nodes in the input layer. And in my output layer, there is just one output. And I have WJs, which are the weights connecting my inputs and the output. So how do we pass this input to the next layer? So first thing you should do is take the linear combinations between your weights and the corresponding inputs. And then you have to add this bias term. So it will actually make sure that your output is as close as possible to the original output that you are looking for. And this, what you have inside this big bracket, is also known as the weighted sum. So finally, to compute the final output y of x, you have to take the composition between your activation function, which is defined on your output layer. So take the composition between your activation function and this weighted sum. So this activation function, there are actually a huge list of activation functions. So there's no universal theory to actually tell you which activation function that you should use. So this is basically trial and error. Now, this can also be formulated in matrix notation. So I will be using this notation in my upcoming slides. And my activation functions are going to be rational functions. Now, using rational functions as activation functions, it is actually not new, but people relatively very recently, they actually started using rational functions as activation functions. So I have only included just one reference here where they actually use low degree rational functions as activation functions. Now, how do we train this simple neural network? So suppose you are given a training set which has capital N number of samples in this training set. And for each set of inputs, you have a desired output. So for each set of inputs, you have just one desired output. So to train this network, you have to actually minimize the error between the outputs coming from your training set and the output that the network computed. So you have to minimize this error in some sense. So the most common loss function used in neural networks is the mean squares loss function. So the popularity of this function is basically due to the fact that you can actually use simple optimization techniques such as gradient descent to find the weights and the bias of this network. So you try to minimize the error between the desired outputs coming from your training set and the output computed by your network. Now, we are actually going to use a uniform approximation based formula for the loss function. So we try to minimize the worst error. And again, this is actually not new. People use this one, but they actually did not know when to use this formula. So in this paper, we demonstrated that this uniform approximation based formula is actually beneficial if your training set is either small but reliable, or if you have underrepresented points or underrepresented classes in your data sets. Now, least squares approximation, it actually tries to take the average. So it actually ignores these smaller groups, treating them as outliers. But for uniform approximation, it will actually take these underrepresented groups as valid points. So in many cases, these outliers are actually not really outliers. They are valid points. They belong to an underrepresented classes. So uniform approximation actually makes sure that we are actually taking the, we are actually considering these underrepresented classes as valid points. Now, about the small training data sets. So this type of training data sets, very small data sets, are actually available in practice. So if the labeling of the data set is done manually, or if the data are produced by a very expensive procedure, so in those cases, very small training data sets may be available, specifically in medical fields. So if medical doctors have to manually check some kind of a signal and label them, so it's actually very costly and time consuming. So in those cases, there will be a very small data sets available in practice. So I have included just one reference here where they actually talk about very expensive procedures where they could only prepare a very small data set. The size of the data set is actually very small. Okay, now let me actually put everything together. So activation functions that I am using are rational functions, but more importantly, I am going to use 1 degree rational functions as activation functions. So now this is my loss function, right? So I have A0, A1, B0, and B1. They are the coefficients of this rational function, and I am going to fix them by the best uniform rational approximation to the Rayleigh function. So this Rayleigh function is another activation function. This is actually not new to us. So this is actually the maximum between 0 and x, where x is between -1 and +1. So you take the coefficients of the rational approximation to the Rayleigh function and you plug them here, so that you fix the coefficients of this rational function. So once these coefficients are fixed, your loss function actually forms a quasi-convex function. So if you do not fix them, you lose the quasi-convexity. So now, since my loss function is a quasi-convex function, I can actually use bisection method to find the parameters of this network. And at the same time, we have a ratio of 2 linear functions here as my approximation. Therefore, the corresponding optimization problems appearing in this network are actually they're actually equivalent to the optimization problems appearing in the generalized rational approximation problems. Therefore, we can use differential correction method to find the weights and the bias of this network. Now, if you want to increase the degree of your rational function, even though you fix the coefficients of your rational function, the corresponding optimization problems will be very hard to solve. So as a preliminary study, I'm going to stick with 1 degree rational functions here. Okay, now moving on to the experiments with data sets. So I am going to use this data set, Sony AIBO Robot Surface 1 data set. So there is this robot, a small dog-shaped robot called Sony AIBO, and it has multiple sensors in it. So in the experimental setting, they actually let this robot to walk on a smooth surface like on a carpet. And also, they actually let this dog to the robot to walk on a hard surface like cement. So in class 1, we have data when the robot walked on carpet, and in class 2, we have data of this robot when it actually walked on the cement floor. So we have 2 different types of signals here. Now the main goal is to distinguish the type of floor that this robot walked on. Now I have just 20 recordings in my training set, and I have 601 recordings in my testing set. So my training set is relatively smaller than the testing set. So now you know why. And we have just 6 recordings coming from class 1 and 14 recordings coming from class 2. And in the test set, we have 343 recordings coming from class 1, 258 recordings coming from class 2. Okay, now these are actually the classification accuracy results for testing set. So these percentages, they are actually the classification accuracy results. So let me explain this table to you. So in the second column, we have classification accuracies computed by the MATLAB toolbox. So there is this toolbox in MATLAB, which is actually called the deep learning toolbox. And the loss function that it uses is the least squares formula. And for our experiments, we actually use the default activation function, default activation function on the output layer for this MATLAB toolbox. And in the next 2 columns, we have uniform approximation based loss function and 1 degree rational functions as activation functions defined on the output layer. And to optimize the weights and the bias of this network, we use bisection method and the differential correction method. Now in this second row, we have original training data set where we have just 20 recordings. So when we use original data set, bisection approach actually computes the highest classification accuracy compared to the other 2 methods. And then we have reduced training data set. So in this reduced data set, what we do, we take our original training data set and randomly select just 10 points from this test, from this training set, and then compute the classification accuracy. So again, bisection method has the highest classification accuracy. And then here we have class 1 underrepresented. So in this case, what we do, we take all the points coming from class 2 in the training set and select just 2 points randomly from class 1. So my training set now just have 14 plus 2, that is 16 recordings in the whole training set. But class 1 is actually underrepresented because there are just 2 points coming from class 1. So again, in that case, bisection method has the highest classification accuracy. And then in the last case, class 2 is underrepresented. So again, we take all the points coming from class 1 along with just 2 randomly selected points coming from class 2. So we have just 8 recordings for the training set, and class 2 is now underrepresented. Okay, now we actually expect the bisection method and the differential correction method to perform not exactly, but at least as close as possible, right? So, but at the same time, differential correction method does not compute high classification accuracy. They are not even close to, they are close, but not as close as we want. So this may be due to the fact that differential correction method uses a different normalization condition, because it actually forces all the parameters of the network to be within the interval -1 and +1. So this may be the reason here. Okay, now we are coming to the end of the talk. So let me summarize everything. So my talk was based on, So my talk was based on this paper, which is still under review. So there are many experiments if you are interested in this. So what we did here, we used 1-degree rational functions as activation functions in a very simple neural network, which has no hidden layers, and there's just one output node in the output layer. So my loss function is based on uniform approximation. And when you fix the coefficients of this 1-degree rational function, the corresponding optimization problems appearing in this network are equivalent to the optimization problems appearing in the generalized rational approximations. Therefore, you can actually use bisection method and the differential correction algorithm to find the weights and the bias of this network. Now, our numerical experiments performed on classification problems confirm that bisection method returns superior classification accuracy results. So there are many future research directions here. You can actually try to increase the degree of your rational activation function and try to solve the complex optimization problems appearing in the network. And at the same time, maybe you can find another way to fix the coefficients. And of course, we can actually look into the differential correction method a bit more and see what's happening in there. So there are many future research directions as well. Thank you very much for listening.
Thank you very much, Vinesha. Are there any questions? We have about 7 minutes, so some time to ask questions. I don't see anybody raising hands, but there's a lot of people. I think, Vinesha, your talk so far is the most popular talk. Oh, Nadia has a question. Nadia, please go ahead.
Yeah, okay. All right. So thank you very much. Vinesha, very good talk. So I just should say that I'm Vinesha's supervisor, but this is her work. I didn't touch it, so that's why I have a right to ask questions, right? Vinesha, so do you think that, well, actually I have 2 questions, right? So the first question, do you think that just based on your experiments, I don't talk about any theoretical background here, so just numerical experiments. So do you think that somehow if you have very few points, then uniform approximation is better from the point of view of overfitting, so you can avoid it? If you have a lot of data, then it's better to use least squares because after quite a few iterations, it probably would compute something better, more suitable to apply the testing data which you didn't see before. So do you think this is a kind of impression your numerical experiments give you?
Well, yes, actually, because I actually did not include the included all the experiments here. So in the paper, I have some more experiments where the testing set has some overfitting in it. So, but at the same time, for the very small training data sets, bisection method actually computed a very small objective function value. So there were no overfitting at all. But when it comes to the testing set, yes, there were some overfittings happening.
Yeah. So, and the second question. So basically, there are some rigorous mathematical results about the choice of activation function. In particular, they started with sigmoid, and then they extended that actually there is a much broader class of functions. And then after all these recommendations, so they use ReLU, which doesn't satisfy actually all these recommendations, right? But it works well, and people are happy to use it. So I didn't have time to write carefully your activation function when you do the approximation, but I think your function is actually satisfying. So for example, the requirement to be bounded, right? So ReLU will grow. So, yeah. But I think your function actually will be bounded. So maybe your activation function is just a better choice than ReLU. What do you think?
Well, I think I should agree. I think this is actually a better better choice than ReLU function, but at the same time, so in the previous previous researchers where they actually used rational functions as activation functions, they did not fix these coefficients. But they did, they initialized these coefficients by the coefficients coming from the best rational approximation to the ReLU function. And then they actually let these coefficients to learn while they train their network. So that is what they actually did previously, but we actually fixing this coefficient because we need the quasi-convexity of this objective function. But at the same time, I think it is actually a better activation function than the ReLU function. And in fact, there is actually a paper, I think it was published in 2017 by Telgarsky, and he demonstrated that neural networks with ReLU activation functions and rational functions actually approximate each other efficiently. So I think instead of using ReLU functions, rational functions are actually a better alternative. Yes.
Okay, thank you. Thank you so much.
Any more questions to Vinesha? I guess I have a very small technical question. So you have shown some results, and there's an improvement when you're using your method and your objective function over the MATLAB toolbox.
Yeah.
So I guess that improvement is because of a different objective function, right?
Yes. Yes.
But then why do you have a difference between the bisection and this correction method? Because that's the same optimization problem with the same objective.
Yes, even though the objective function is the same, they use different normalization conditions. That is why I guess actually that is why the difference actually happens, because for differential correction method, it actually forces all its parameters in the denominator to be within the interval -1 and +1. But for bisection method, you simply can fix just one parameter of the network so that you don't your denominator won't be 0. So I think those two normalization conditions are different, and due to this fact, differential correction method computes lower classification accuracies than the bisection method. But at the same time, differential correction method has better classification accuracies than MATLAB toolbox.
Oh, cool. That's very interesting. Thank you very much.